upset in there. And let's just do a process upset of 5. Just so you can see, I don't want to give too much of a deviation, but just so you can see this process working. And again, now it's based upon your time, your integral, and the way the error is being calculated, your proportion. A lot of people would have shot up their proportion really high to get this accomplished. And don't get me wrong, you can do that, but alright, so in this video we're going to show you how to program a PIDE instruction, and we're going to show you how to do this in function block. Now, with that said, we're going to do the logic a little bit different, and we're going to simulate the whole thing, right? So we're not going to have any real world devices, in that we don't have any kind of real world inputs or a real processor. We're going to show you how to do this with an emulate process and simulate the whole thing. So you can actually follow along at home, and you can also use a real world processor if you want. Now, just to briefly talk about that, I went ahead and made the program. So what I've done in the program, and I've come over here and put this in slot 14 of the Studio 5000 Logic Emulate, which is what I'm currently using. And I am using a Logic Designer, the Studio 5000 version 31. Now, the version 31, that's the only reason I chose that version, is because that is the emulate that I currently have. So with that said, I went ahead and made the processor. To save us some time, I went ahead and made the program, but I haven't done any programming in it just yet, right? So let me just show you that. In the main routine, I actually have nothing in here. There's no tags whatsoever in the program level or at the program or controller scope tags, right? So I have done one thing, and I've changed the task. I've changed the task over here, the main task. I've changed it from continuous to periodic. Now, I'll explain why I did this a little bit later when we set up the PIDE instruction, but just note that the way the PIDE instruction actually scans itself is actually, you can base it upon your periodic task, right? So I'll actually show you that in just a second. So we put that at 47 milliseconds, and I changed the name. I've just changed the name basically so I can understand the timing behind it if I were to look at it at top level, right? So first we need to come in here and add a new routine. Alright, so we're going to come in here, we're going to call this PIDE, and use your drop down here, the type. You can have ladder logic, sequential function, function block, or structure text. We're going to be doing this in a function block diagram, so we're going to select that. Now, it's currently not going to come in as a scannable routine. Again, we're going to go ahead and leave it like it is. So in the scannable, to make it a scannable routine, anytime you add a routine in, you got to understand the way the process works, right? You have your main task, which is automatically going to scan the main program. The main program is going to scan the main routine, and the main routine, you come over here to get it to scan the new routine we just added. We're going to add in a JSR, so JSR, and then we're going to come over here and select the new routine we just added. Okay, so we'll come over here. Now this is scannable. We'll assemble all edits, right? Finalize all edits, just to get that where it's a scannable routine. All right, so now we need to actually, and being that I had to do that is only because I was already online, right? I already downloaded the processor. So now let's go ahead and add in the actual instruction. Now, if you're not familiar where to look and get this actual instruction from, this PIDE instruction, you're going to go up to your top toolbar, and you're going to select the word process, and then you're going to come over here to PIDE, and you're going to drop this down. Now we're going to change the name of this, right? So we're going to edit the name. We're going to call this simulation loop. Okay, so that's what we're going to have, and we're going to have that in there. Alright, so got this in here. Now we're going to add in a auto tune. We're not going to auto tune just yet, but we're going to add in a tag for this. Call that auto tune, and sometimes it won't populate in there, so you got to come back in here and select it again. Not a big deal. Alright, so let's go ahead. We've added this in here. So I want to briefly talk about the way I was describing why I changed the main task real quick. Is the main task in the first, if you pop open the little tab of the PIDE instruction, the timing is what I was referring to. So the timing mode can be set to periodic, oversampling, or real time. Then the most, I would say, used atmosphere would be the periodic task. So the periodic task is where you would change to actually control the way the calculation of the PIDE instruction works. You have two different types of calculations. Either one of those calculations would get updated based upon the time you have in your PID or your task level, right? So understand the periodic task right here is associated with the periodic task up here. It's very much a thing that I guess is slightly confusing when you first start out and you first get used to using these instructions, right? So just understand that that's the way that the calculation, no matter which calculation you choose, is going to be used. So we're going to click apply here. Now we haven't added anything, so first let's actually set that up real quick. So we're going to use this. Let's just say, for instance, we're going to use a process like a AC unit for your house. So the high set point would be something like, let's just say 95, which would be extremely hot, don't get me wrong, but then the low temperature would be like 60. And our PV, our max set point for our PV, our output, would be 100% and then 0%, right? So the CV can go from 100% to 0%, and then we're going to have our process, our set point right here. Alright, so we'll click that real quick and get that in there. Now we're not going to do anything else as far as this right now, but we'll just leave that in there. Alright, so we need to come in here and add a few things like our set point. Alright, so our set point, well, let's just say 68 degrees, because most if you are generally speaking, depending upon where you live, the house would be, if you're in a hot environment, you want it about 68 degrees, 70 degrees, something like that, right? So we also need to come in here and throw in another thing, which is we're going to set a 1 to the prog request, and we set a 1 to the prog auto request. Now, with that said, when we're hard coding it like this, we don't have the ability to auto tune, because auto tune is done in manual mode. Just keep that in mind. We're going to come back and do that later, but let's go ahead and add a few more things. So we're going to go back up to process. We're going to add in a couple things to help us simulate the process. Now those couple of things, one would be a lead lag. Okay, we'll call this lead lag, and then we'll edit the name. We'll just call this lead lag, just like that. Give it a name, and we're going to put that to the CV, or the PV, I'm sorry, the process variable. Process variable is your input going back that will actually give the raw data to the actual PID, so it can adjust itself based upon the calculation. Alright, so another thing we're going to put in is our DEDT, which is our dead time. Okay, so we're going to put that in here, and we're going to call this, we're going to rename this, we're going to call this PIDE delay. So this is going to be a delay for a delay reaction. So how does this work? I'll show you. So the PIDE, or the actual DEDT instruction, works very similar to, let's just say, a process, natural process loop, right? Where a natural process loop would have any kind of a delayed time, or a buffer time, or some kind of time that the real world reaction would happen. Say you're adjusting a valve and the flow has to move, or you're adjusting, let's just say, the temperature, and the temperature has to change in your readback, your delay readback from wherever your sensor is, or the process has to adjust. There generally is some kind of time in there that there's no activity. What we're going to do is simulate that process, and we're going to call that the dead time. Okay, so we're going to put in about 8 seconds here. Okay, that seems like a lot, but it's really not. And then that's all we're going to do for this dead time. Now, with that said, we need to have a storage array. Okay, so the storage array, what it does, and I'll show you this, is we're going to come in and create a new tag, and we're going to call this PIDE array. Now, in that array, we're going to have to have a dimension. So the dimension is how, like, the rate of time you're using based upon your actual time that you're actually scanning. So the scan rate is currently 47 milliseconds, and we're going to be putting 8 seconds. So we need to have enough data in that array to actually populate that. So all we're doing is collecting data and then allowing that data out. So what we're going to do is we're going to put this about 300. All right, so that's 300 reels. So that gives us enough bit. Let me show you how the way that works too. Once I start scanning and this process starts scanning, it's going to say we have 300 elements, and then we're required to have right now 1 element because we're not scanning. Once we start scanning, it will be required to have more elements because we're going to be set at 8 seconds. And I'll come back and show you that in just a second. All right, so another key thing too in this lead lag, and I want to show you this, drag this out, and you can see that there's a lead, a lag, and a gain. Now the gain is really cool in this environment because what you can do is you come in and put like 1.2, and that acts as a multiplier. Okay, acts as a multiplier for what you're doing. You can also put a lead or lag in here as well. We'll put 5 seconds of lag, which just seems like a lot, but if you think about it, that's a complete lag of, let's just say, or delay, if you would, in the whole process of 13 seconds, which all this is based upon seconds, not milliseconds. It's based upon seconds. Okay, so just keep that in mind. So we have our delay in here, our PIDE delay. We have our lag. We're going to come in and add another element in here, which is going to be a math feature. Let's go ahead and add this in here, and we're going to put a math feature so we can put in a hiccup. So I want to put a process hiccup in here, and that's what I'm going to actually call the tag. I'm going to process hiccup. Okay, and this is going to be, we're going to have to change it from the data type from a dent to a reel. No worries. All right, so we're going to put that and add that in here. Now currently at 0, no matter what it is, it's going to add against 0. It's not going to be anything. Now we need to drag the destination over here, and we're going to pin it from the destination to the input of the DEDT. Now we're going to right click on this, and we're going to assemble the data available, right? So also too, let's change the name of this. Let's change the name of the add to process adjustment. If my typing would work. Okay, all right, and it still didn't have a problem. Let's see where we're at. All right, cool. Adjustment. All right, we have that in there. So process adjustment. So I like to kind of line these up, and sometimes they will, sometimes they won't come into the actual process where you can see them. So let's actually assemble this. Now first, before we assemble this, what I want you to know is it's going to try to go ahead and get to the point that it's at. We don't currently have anything, so we don't have any kind of loops in here. Let me explain to you the way the proportion and integral and derivative work real quick. Now we're going to be doing this first in a independent mode, and so you have two different types of equations. You have the independent and you have the dependent. There's two different types of the way the equation would scan and make the correction that it needs to make, right? Let's go ahead and talk about that. So you can right click on the PID instruction, and you can open up instruction help, and then we'll come down here to the very bottom of the instruction help, and it talks about, and I know this is kind of scanning through real quick, but I want to get to this point. All right, computing. All right, so let's talk about that. So in the independent, I want you to note, even the Rockwell documentation says this, each term in the algorithm, the proportion, the integral, and the derivative has a separate gain. changing one gain only affects the term and not the others. So with that being said, it's easier to put in a independent PIDE because you can understand if you're changing the proportional, which in the equation would be the KP and then the time and the error, right? So this would be between the plus sign and the plus sign is the P, which is proportion, and then the next plus sign would be the K over the time again and the error, and then you come over here and that would be from plus sign to plus sign is the integral. Then next, the very last thing would be the derivative, right? So in the equation, it's independently, just like the name says, independently changed, right? So you change one variable in the way the equation, just upon like regular process of mathematics, right? The way the process is worked out and the way that actual equation is written, that's the way it's going to work. Now, contrary to that, on the dependent, if you change one, you change all three terms. Now, why would that be said? Is because the way they have it working, right? The way they have the equation written, they have brackets around it, and they're doing the equation slightly different. So again, the P would be working different than the I, and then the I would be working different with the derivative. Again, when it comes down to it, it's just understanding the way the system works, right, and the way the two work. Right now, we're going to be concentrating on the proportional because it's easier to break down the proportional, P, the I, and the D, right, the derivative. So let's go ahead and close this. All right, so let's talk about that real quick. We have nothing. We have our set point put in here. We have our set point limits in here, right? We don't have anything as far as the way. Now, how you actually change the equation type? Well, you would just change this right here. If you notice right here, it changes the integral to minutes for repeat. Now, the independent is slash minute, right? So if we don't put anything in here, it's not going to react. So it's very much an easy thing to understand. Now, let me explain something to you. One would think too that if you have that most people just come in here, put a proportional in here, and then the PID would work, right? We're going to leave this completely blank right now, and we're going to assemble this, right? So let's come over here and let's make their final edits. Now, it's not going to change a single thing right now because we don't have anything in here. So let's go ahead and add something in here. Let's go ahead and add a little bit of, let's just do, being that 90% of people always think the integral does absolutely nothing. The integral is based upon the time and the scan. So if you have in our situation, we have our system scanning every 47 milliseconds. So if we put in a integral of 5, let's just say 5, then it's going to start adjusting. Okay, and one would think that, well, this might not get to set point, right? It may or may not get to set point. Now you see the lead lag start working. See that lead lag start working? And that's just because of the simple fact of the way. So the way this currently works too is what's coming in as a process variable is going to be the actual, that's going to be the actual PV in the set point, right? That's going to be the actual. So we can actually come over here and add a tag out here called actual. Now currently we have, again, we have the actual integral in there. We don't have any kind of proportion. Let's throw a little bit of proportion in there just to kind of give you a base implementation. And let's come in and throw some proportion. Now we throw in proportion, it's actually lowering it back down. So you see that? It's actually trying to control it a little bit better, right? So it's still a little bit sluggish right here. Now we're just manually tuning this real quick, just to throw in a manual tune. The base implementation of what I'm showing you right here is for you to be able to program this yourself. And we're going to build a trend real quick and show you how this works. But I'm going to come over here, and while we're doing this, so you can better understand, if we're going to go to assets and we're going to go to trends, we're going to make a new trend. We're going to call this PIDE, and let's just call this independent. All right, so let's add in our tags. So we come over here and we change our program level to program, and let's add in our process, our loop. And I think I have both of these. For some reason the name is coming in, so let's copy this. What level is this? This is the program level. Okay, and new trend, and then we'll call this PIDE and PIDE and independent. Alright, so we're going to go, this is in the task level, is where the program or the tags are. So we'll come over here and add this in here. Now we can see what we're in. Let's just see, this is that's the one I misspelled if you can imagine that. So we're going to come in and get our PV. So let's get our PV, and let's get the, let's get this out, right, and then add that in there. So let's get our PV as well. Set point is something we need, and let's get our error. Let's get our PV. PV is what we want to actually see in the trend. I think I passed it. I am notorious for passing it, so forgive me for that, but we will find it. Let's CV, 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 and the PV. It seems like it should be right in here. There we go. PV. Add that in there. Alright, so the next section, we're going to come in and change a couple things in this. So first we want to come in and change our pins. I like to get these a little bit darker. So let's get a 2, let's get a 2, and let's get a 2. Let's get a little bit darker of a line. And let's come over here and change this back to a white so you can see it. Alright, so let's apply that. Now it's easier to see. Change our timing. Our x-axis is our timing. Let's change this to 45 milliseconds. And then we're going to do a custom. Now our custom is going to be -10 to 100. It's perfectly fine because our set, what we're trying to do is within our set points, right? But we also want to keep it where we're within the actual CV's components, where the CV can go from 0 to 100. The set point can go from, the set point is currently at 68, but we can take it from our limits, which is 95 to, if you remember, 95 to 60. Alright, so let's get that, add this in here, and we can actually change a couple different things. We can change the grids. Let's see, major grids, minor grids. Let's add 5 and get that just looking like that. Alright, so let's come over here, see where we're currently at. So now we have the pins in here, and we can see that the current PV is right at its set point. So it's right at its set point. The reason you can't see the set point. Let's actually throw in a process variable. So this is currently, you see this right here, and let me pop this down so you can actually get a better understanding of the real. Okay, so this would be the actual temp. Okay, so that's the actual temp, just so you understand the way that works. The actual temp is your PV coming in, right? So the PV again is going into your PID loop, your PIDE loop, and then the CV EU is coming out, right? So that's the adjustment that the equation is actually doing to get it to the process. Now let's throw a hiccup in here. Let's just say 5. So now the process is going to start, depending upon our dead time over here, is going to start changing, right? So now we're starting to change, and let's go into our loop, and you can see our loop coming out, right? So our current PV, which is our actual, is the red line, And let's get those a little bit thicker so you can see those. Let's get the pins a little bit thicker so you can see those. Drop down, do a 3, 3, 3, 3. All right. So we'll change that, and you see it kind of overshot a little bit here, which is perfectly fine. But we're just trying to give you an implementation. So it kind of went out of spectrum, which is our process loop. It kind of came down, and then it overshot. So you can see the way that works. So hopefully that's very. And I don't know if this white's helping. Maybe the white would be too much, or maybe the axis, the grids are too much. I think that, to me, that looks better. You can kind of see that line. Okay, so with all that said, we're seeing now it's at set point, but we overshot a couple times in here, so let's change this a little bit. Now in this process loop, let's change this to 15. Now again, changing the integral that high, normally people would be like, well, that's just not what we do. We change the proportion, right? The proportion is what we should change. But just keep in mind, if you change one, you need to change the other. So just keep that in mind. Now our process is settled out. It's at our set point. Our set point is at 68. Our process is actually 68. Let's throw in a process hiccup of like 20. Okay, so a huge process upset, and I'll show you the data coming in just a second. But let's look at how the loop's working. Okay, so let's see, it's going out of spectrum, right? Because we put in a process upset, so it's understandable that the CVEU would be out of proportion, right? And then the PV, again coming back, would be out of spectrum. You see, we overshot really bad here. So let's see. So it's trying to find itself. I'm just showing you that how much influence that integral has. So you see, it's almost where it's swinging out of control, and it is swinging out of control. So let's get this back in control. Let's get this. So we've maxed out, right? We maxed out where we can't control it. So let's get this back in control. Let's just say this is 5. And let's say this will be, let's just go in here and change the proportion to 45. See how aggressive that would be. Okay, so we made a change. It's coming back down, and let's see what it does. And it's still, actually, the red is our PV. It may take a second with this dead time to actually get back in line or get the loop back in. So this is currently in the process of what we're doing with this dead time. It's trying to find itself. You see that the process is trying to find itself right now, and it's actually recovering pretty good compared to where we were. We were way out of proportion. And again, what can really help is a nice auto tune, but we're not in that point yet, right? So we want to simply understand the way that your process would be working. Now, what I mean by that is how much the independent, or how the integral works based upon the proportion. So let's let it settle out, right? Because it's currently just about settling out, and it's currently adjusting itself, fine-tuning itself back in. All right, there's that. So this is amount that, again, the dead time, to talk about how many. I want to show you that too, the process of the dead time, so you understand the way that works. So if we went over here and we looked at the data coming in, every 8 seconds this data is getting updated, right? Every 8 seconds this data is being updated. Now let's just merely change the dead time from 8 to 4. So we're 8 to 4. Now that's going to speed up this area right here, right? So let's do a process hiccup of 20, and I'm going to show you the way this works. So let's go back into monitor tag, and you'll start seeing this updating. So every time this comes in, you see the data is updating. That's the beauty of the way that actual dead time instruction works. Is again, it's based upon 4 seconds. So coming in here and just changing our dead time alone really affected the way the PID worked. So the process, this is a real strong implementation of a real powerful implementation to show you that timing is everything. What I mean by timing is the way your timing is set up based upon the real world processes. So all we did was change the dead time from 8 to 4, and you see it's a nice trend up. I can repeat that process again. Let's put it at 15. Let's put a process hiccup of 15 in here, and I'll let you see that. So this is where the process is going to come in and hiccup, and then I want you to see it coming back. Now what we're simulating here is, again, the process upset, and we're simulating a process getting back into where it needs to be. But we're also too explaining the dead time or the lag time of the actual process being, in play, right? So if there's only 4 seconds, we changed it from 4 seconds to 8 seconds, which was a total of actual 13 seconds. We changed it from 13 seconds. We took 4 seconds off of it, so now we're only a 9 seconds lag. And so our whole system has a 9-second lag. So you have to calculate the actual lag of your system, and like if you have a really complex system and it takes a long time for reactions to happen, you need to make sure you tune accordingly for that, right? And I'll show you the exact same thing. All I did, just in case you wanted to know, is change the process variable, or I changed the DED, the dead time, from 4 to 8. Okay, so it's going to be completely still right now. But if I do that again, okay, if I do a process hiccup again, I take it to 0, and this is why this code is so powerful, because you can see what you're doing, and you can actually emulate and simulate what you're doing. So you see it's starting to react now. Okay, now I would not suspect that this is going to fall right in place. Actually, we did put in more proportion, so the proportion may help it a lot, but when it comes down to it, the timing of everything did help it a lot too. So the timing, this should overshoot a little bit and then come back and find itself. So it's overshooting, which is not what it did just a second ago. We didn't mess with any of the tuning, right? This is just showing a process change. A process change, which would be like more of a time delay, right? And the powerful point to this is really what I'm trying to enforce here is the way the way simulating this code works is giving you a solid implementation of how much time versus error do you have. Your time versus error is how your PID is going to react. You see that? So we added the 4 seconds back in. Now I'm going to take it back out. I'm going to take it back out, and I'm going to show you that process one more time. Okay, so this is 4 seconds. Now I'm going to put it at 4 seconds. And don't get me wrong, we're still doing our times 2, our 1.2 times. So we still have that in there. Now let's put that process upset back in here. Okay, so now we're going to see the process get upset again. So all this is doing is changing the reaction time of the field devices, if you can think of it that way, right? In the case of an actual AC unit at your house, you're probably not going to have, you could have a large swing in, let's say, your temperature outside versus your temperature inside, or you could have, which is, one of those things, or maybe even something along those lines, like a valve or something shutting or opening not too quickly or something like that. Now this could be based upon, now in the real world you would have something like, and let's just say for instance this could be used for well, really anything, steam flow. It could be used for it could be used for like piping flow, or the flow of a product to something, heating of that product, cooling of that product, the flow of that product. If you want to set flow rate of that product, it could be anything. Like, for instance, I mean, there's a million and one reasons why a PID loop would be implemented. Okay, so with that said, now what if we wanted to tune in that really aggressive loop, right? Let's see what we can do. So we can, I would think we would need to, if we want to have this back at 4 seconds or 8 seconds, then we could actually, and I think it's a little bit aggressive, in my opinion. So let's take this down to 3, and let's actually take the integral up to 15 and this down to 1.5. So again, like I said, if you adjust one, you adjust the other. All right. So you would almost think, well, why don't you just use the dependent? Well, the point of it is showing the difference. The independent is really a powerful tool when you're trying to show how the system works, right? How a PID works, especially upon dead time, especially upon the time of the process loop, right? Dead time in our environment is just showing the process loop. So we're overshooting a little bit, okay? But you see our swing right there. So we are overshooting. Let's see how bad the overshoot is. So one would think that the amount of integral I have right now, the thing I need to do would be to lower the integral or either increase the proportion. Now I'm going to show you that same exact thing, because see, this is it's gonna eventually find itself, but it's just going to take a little bit of time. So let's just look at this top loop. It's actually getting right about, it's adjusting very, very, very slow. So let's go back into our PID loop, and we can either cut our proportion up. We'll cut our proportion up, and let's see how well that helps it. Okay, so let's see how well that overshoots. That line should get a little smaller. And let's see, it did, but not much. Right? Now this should come back down. It should start shrinking a little bit as it goes. So we didn't really change it too much. So let's come over here and change it a little bit more. So let's go 5. So that's 0.55. Okay, so that's changing our proportion that much more. And let's see what it does now. Now proportion, again, versus how much integral we have, there's a lot of, and again, integral is time. So the time rate of our task, I can actually show that in another video, the timing difference. But again, when it comes down to it, we're going to get this loop right back into spectrum. So let's actually come back in. Let's adjust this a little bit. Let's say 7. And it really, in my opinion, really shouldn't be that high. But let's just see. Alright, so it's finding itself a lot better now. It's going to overshoot a little bit. But again, and natural progression being 1 degree off of where you're actual at, it's not really that bad. But in our environment, it is kind of bad. So let's come over here. Let's change our proportion back to, let's just say 1, and let's just change this back to 5. Okay, and let's change this. This was what did we put this at? 4 seconds. Okay, so we're at, this is the 1.5, and this is integral of 5. All right, so currently we're right on target. Still a process upset in there, and let's just do a process upset of 5. Just so you can see, I don't want to give too much of a deviation, but just so you can see this process working. And again, now it's based upon your time, your integral, and the way the error is being calculated, your proportion, a lot of people would have shot up their proportion really high to get this accomplished. And don't get me wrong, you can do that, but if you just have a proportion, you don't have an integral, it's not going to help you. So that did undershoot just a little bit. So let's take our proportion up a little bit. Let's take our proportion up just a hair. I think 2. Actually, let's put 2 and then 0. And let's do that again. So then we'll go to 10. So you see how powerful this code is, right? So the cool thing about how powerful the code is it shows you, again, what you're doing, and it teaches you what you can and can't do, right? And it actually shows you the process of real-world devices and how long it takes to do that. Now, again, I started off just throwing in random numbers. I started off with a really good implementation, but when it comes down to it, when you're putting this in, start off with something that's thrown off a little bit. So even that said, so this is right at that set point. But again, when you can see that right there is adjusting itself, and again that whole deadband, the dead time, and then the actual lead lag. If I take out the lag of this, it will change that dramatically as well. Also, if I change the periodic task, it will change it greatly as well. So again, coming back, we are in Spectrum. Now what I want to do is in the very next video show you some different things, like just use proportion or just use integral, and show you the difference between the two and kind of give you a base implementation of that. So with that said, let's go ahead and conclude this and carry on to the very next video.